So I'm curious about how much acceleration does a pilot or the pilot and the plane experience when they need to take off from an aircraft carrier. So I looked up a few statistics on the internet. This right here is a picture of an FA-18 Hornet right over here. It has a takeoff speed of 260 kilometers per hour. If we want that to be a velocity, 260 kilometers per hour in this direction if it's taking off from this Nimitz class carrier right over here. And I also looked it up, and I found the runway length, or I should say the catapult length, because these planes don't take off just with their own power. They have their own thrusters going, but they also are catapulted off so they can be really accelerated quickly off of the flight deck of this carrier. And the runway length of a Nimitz class carrier is about 80 meters. So this is where they take off from. This right over here is where they take off from. And then they come in and they land over here. But I'm curious about the takeoff. So to do this, let's figure out let's just figure out the acceleration. And then from that, we could also figure out how long it takes them to be catapulted off the flight deck. So let me get the numbers in one place. So the takeoff velocity, I could say, is 260 kilometers per hour. So let me write this down. So that has to be your final velocity when you're getting off of the plane if you want to be flying. So your initial velocity is going to be 0. And once again, I'm going to use the convention that the direction of the vector is implicit. Positive means going in the direction of takeoff. Negative would mean going the other way. My initial velocity is 0. I'll denote it as a vector right here. My final velocity over here has to be 260 kilometers per hour. And I want to convert everything to meters and seconds just so that I can get my, use it at least for meters so that I can use my runway length in meters. So let's just do it in meters per second. I have a feeling it'll be a little bit easier to understand when we talk about acceleration in those units as well. So if we want to convert this into seconds, we'll put hours in the numerator. 1 hour, so it cancels out with this hour, is equal to 3,600 seconds. 3,600 seconds. I'll just write 3,600 s. And then if we want to convert it to meters, we have 1,000 meters. 1,000 meters is equal to 1 kilometer. And this 1 kilometer will cancel out with those kilometers right over there. And whenever you're doing any type of this dimensional analysis, you really should see whether it makes sense. If I'm going 260 kilometers in an hour, I should go much fewer kilometers in a second, because a second is so much a shorter amount of time. And that's why we're dividing by 3,600. If I can go a certain number of kilometers in an hour or a second, I should be able to go many more meters in that same amount of time. And that's why we're multiplying by 1,000. But you multiply these out, the hours cancel out, you have the kilometers canceling out, and you have 260 times 1,000 divided by 3,600 meters per second. So let me get my trusty TI-85 out and actually calculate that. I have it over here. So I have 260 times 1,000 times 1,000 divided by 3,600. Divided by 3,600 gets me, I'll just round it to 72 because that's about how many significant digits I can assume here. 72 meters per second. So all I did here is I converted the takeoff velocity. So this is 72 meters per second. This has to be the final velocity after accelerating. So let's think about what that acceleration could be, given that we know the length of the runway. And we're going to assume constant acceleration here, just to simplify things a little bit. But what does that constant acceleration have to be? So let's think a little bit about it. The total displacement, I'll do that in purple. The total displacement is going to be equal to our average velocity while we're accelerating times the difference in time, or the amount of time that it takes us to accelerate. Now, what is the average velocity here? It's going to be our final velocity plus our initial velocity over 2. It's just the average of the initial and final. And we can only do that because we are dealing with a constant acceleration. And what is our change in time over here? What is our change in time? Well, our change in time is how long does it take us to get to that velocity. Or another way to think about it is our change in velocity divided by our acceleration. If we're trying to get to 10 meters per second, and we're trying to get 10 meters per second faster, and we're accelerating at 2 meters per second squared, it'll take us 5 seconds. Or if you want to see that explicitly written in a formula, we know that acceleration is equal to change in velocity over change in time. You multiply both sides by change in time, and you divide both sides by acceleration. So let's do that. Multiply both sides by change in time and divide by acceleration. Multiply by change in time and divide by acceleration. And you get that cancels out. And then you have that canceled out. And you have change in time is equal to change in velocity divided by acceleration. Change in velocity divided by acceleration. So what's the change in velocity? Change in velocity. So this is going to be change in velocity divided by acceleration. Change in velocity is the same thing as your final velocity minus your initial velocity. All of that divided by acceleration. So this delta t part we can rewrite as our final velocity minus our initial velocity over acceleration. And just doing this simple little derivation here actually gives us a pretty cool result. If we just work through this math, and I'll try to write a little bigger. I see my writing is getting smaller. Our displacement can be expressed as the product of these two things. And what's cool about this, well, let me just write it this way. So this is v, our final velocity, plus our initial velocity, times our final velocity minus our initial velocity. All of that over 2 times our acceleration, our assumed constant acceleration. And you probably remember from algebra class, this takes the form a plus b times a minus b. And so this is equal to, and you can multiply it out, and you can review in our algebra playlist how to multiply out two binomials like this. But this numerator right over here, I'll write it in blue, is going to be equal to our final velocity squared minus our initial velocity squared. This is a difference of squares. You can factor it out into the sum of the two terms times the difference of the two terms. So that when you multiply these two out, you just get that over there over 2 times the acceleration. Over 2 times the acceleration. Now, what's really cool here is we were able to derive a formula that just deals with the displacement, our final velocity, our initial velocity, and the acceleration. And we know all of those things except for the acceleration. We know that our displacement is 80 meters. We know that this is 80 meters. We know that our final velocity, just before we square it, we know that our final velocity is 72 meters per second. 72 meters per second. And we know that our initial velocity is 0 meters per second. And so we can use all of this information to solve for our acceleration. So, and you might see this formula, displacement, sometimes called distance, if you're just reading the scalar version. And really, we are thinking only in the scalar. We're thinking about the magnitudes of all of these things for the sake of this video. We're only dealing in one dimension. But sometimes you'll see it written like this. Sometimes you'll multiply both sides times the 2a, and you'll get something like this, where you have 2 times really the magnitude of the acceleration times the magnitude of the displacement, which is the same thing as the distance, is equal to the final velocity, the magnitude of the final velocity squared. What we're assuming this is, so the final velocity squared minus the initial velocity squared. Or sometimes in some books it'll be written as 2AD is equal to VF squared minus VI squared. And it seems like this super mysterious thing, but it's not that mysterious. We just very simply derived it from displacement, or if you want to say distance, if you're just thinking about the scalar quantity, is equal to average velocity times change in time. So far we've just derived ourselves a kind of a neat formula that is often not derived in physics class. But let's use it to actually figure out the acceleration that a pilot experiences when they're taking off of a Nimitz-Class carrier. So we have 2 times the acceleration times the distance, that's 80 meters, times 80 meters, is going to be equal to our final velocity squared. What's our final velocity? 72 meters per second. So 72 meters per second squared minus our initial velocity. So our initial velocity in this situation is just 0. So it's just going to be minus 0 squared, which is just going to be 0. So we don't even have to write it down. And so to solve for acceleration, you just divide. So this is the same thing as 160 meters. Well, let's just divide both sides by 2 times 80. So we get acceleration is equal to is equal to 72 meters per second squared over 2 times 80. Over 2 times 80 meters. 2 times 80 meters. And what we're going to get is, and I'll just write this in one color, it's going to be 72 divided by 160 times, we have in the numerator, meter squared over second squared. We're squaring the units. Meter squared over second squared. And then we're going to be dividing by meters. So times, I'll do this in blue, times 1 over meters, right? Because we have a meters in the denominator. And so what we're going to get is this meter squared divided by meters. That's going to cancel out. And we're going to get meters per second squared, which is cool because that's what acceleration should be in. And so let's just get the calculator out to calculate this exact acceleration. So we have to take, oh, sorry, this is 72 squared. Let me write that down. So this is going to be 72 squared. Don't want to forget about this part right over here. 72 squared divided by 160. So we have, and we could just use the original number right over here that we calculated. So let's just square that and then divide that by 160. Divided by 160. And if we go to two significant digits, we get 33. We get our acceleration is equal to 33 meters per second squared. And just to give you an idea of how much acceleration that is if you are in free fall over Earth, the Earth, the force of gravity will be accelerating at you. So G is going to be equal to 9.8 meters per second squared. So this is accelerating you three times more than what Earth is making you accelerate if you were to jump off of a cliff or something. So another way to think about this is that the force, and we haven't done a lot on force yet, we'll talk about this in more depth, is that this pilot would be experiencing more than 3 times the force of gravity, more than 3 Gs. 3 Gs would be about 30 meters per second squared. This is more than that. So an analogy for how the pilot would feel is when he's, if this is the chair right here, that his pilot's chair that he's in. So this is the chair, and he's sitting on the chair. Let me do my best to draw him sitting on the chair. So this is him sitting on the chair, flying the plane. And this is the pilot. The force he would feel, or while this thing is accelerating him forward at 33 meters per second squared, it would feel very much to him like as if he was lying down on the surface of the planet, but he was 3 times heavier, or more than 3 times heavier. Or if he was lying down, or if you were lying down like this, let's say this is you, this is your feet, and this is your face. This is your hands. Let me draw your hands right here. And if you had essentially 2 more people stacked above you, roughly, I'm just giving you the general sense of it, that's how it would feel, a little bit more than 2 people, that squeezing sensation. So his entire body is going to feel 3 times heavier than it would if he was just laying down on the beach or something like that. So it's a very, very, very interesting, I guess, idea, at least to me. Now, the other question that we can ask ourselves is, how long will it take to get catapulted off of this carrier? And if he's accelerating at 33 meters per second squared, if he's accelerating at 33 meters per second squared, how long would it take him to go from 0 to 72 meters per second? So after 1 second, he'll be going 33 meters per second. After 2 seconds, he'll be going 66 meters per second. So it's going to take, and so it's a little bit more than 2 seconds. So it's going to take him a little bit more than 2 seconds. And we can calculate it exactly. If you take 72 meters per second and you divide it by 33, it'll take him 2.18 seconds, roughly, to be catapulted off of that carrier.